Hello and welcome to Dr. T's Math. In this video, I want to look at some sine waves and cosine waves and link them to harmonics and octaves in music. So recently I have been teaching a trigonometry and a calculus class, and in order to bring things to life, I like to find relevant daily examples that include sine waves and cosine waves and things like that. And it is really remarkable how many of life's processes follow these same basic patterns. And these two functions are just transformations of one another. So I found this article recently, which is comparing the frequencies of different harmonics, and the author even goes into some detail about flute and oboe and violin, how these functions here, these waveforms, are the sums of different harmonic overtones, which are diagrammed out here. And you might notice that it is a arithmetic sequence, starting at the bottom on the right there, 1/6, 1/5, 1/4, 1/3, 1/2, and then 1, or 1 over 1, as an arithmetic sequence for the harmonics. And then up here on the bottom you see these are octaves. And so the low A at the top here, 55 hertz, is half the frequency as the low A, the second one, which is 1/2. And then if we multiply by 2 again, so these are powers of 2, 55 times 2 is 110, 110 times 2 is 220, 220 times 2 is 440, and so on. That is a geometric sequence. So octaves work in geometric sequences, and harmonics work in arithmetic sequences. And so if we wanted to look at how to graph just exactly what we saw there on the PDF here, then use Geogebra or something like that. And I've started up at the top with the longest wave. And so I've got negative sine x. Then we can overlay that with sine x. So we've got negative sine x quantity plus 15 and sine x quantity plus 15. And then that plus 15 is the transformation up the y-axis in order to stack all of these different waves on top of each other. And then the next one, we're just going to add 1 inside the parentheses. So this is negative sine 2x plus 13 now, because our amplitude is 1. The midline is that last value that we've added to move it up the y-axis. So this is, again, negative sine 2x plus 13, and here's positive sine 2x plus 13. And then we'll just go on down the line. Negative sine 3x plus 11, positive sine 3x plus 11, negative sine 4x plus 9, positive sine 4x plus 9, negative sine 5x plus 7, positive sine 5x plus 7, negative sine 6x plus 5, positive sine 6x plus 5, negative sine 7x plus 3, positive sine 7x plus 3, negative sine 8x plus 1, and positive sine x plus 1. And so that's the harmonics from the first until from the bass tone, or what did they call that? Fundamental tone. From the fundamental to the eighth. And it is in the same descending order here in terms of wavelength. The highest wavelength, the greatest wavelength, is on top. And we could do the same thing to create a graph of octaves. Again, noticing that they are just sine waves, that they're harmonics vibrating up and down over some certain frequency or period. And then the flute, they said here, is the fundamental tone plus the first harmonic, so it's 440 plus 880 on there. And we could simulate that by saying y equals sine x sine x plus sine 2x. And that's roughly what that flute looks like. Then the oboe was a little bit more complicated, and with a little bit more time to deduce what formula to input, then I could simulate the oboe and the violin with Geogebra here. But we can see that these are the sums of different sine functions. Getting back to the octaves, so we got y equals sine x and y equals negative sine x as the fundamental octave, or the first octave, that low A, 55 hertz. Now if you wanted to make it 55 hertz, that's 55 cycles per second, our x-axis units would change. In the general mapping of sine waves and cosine waves onto the xy axis, what we have here is this 3.14, that's pi, and then 2 pi, and this refers to the unit circle. So in order to move into hertz, like cycles per second, then our units would change on the x, so we'd have to do a little bit of a transformation on the function. But this gives us a basic idea of what's going on. And then the next one was half the wavelength. So y equals, we're going to get sine 2x. What happens inside the parentheses is kind of backwards. Like if it says 2x inside parentheses, then we're shortening it. And that's because there's twice as much stuff going on in the same distance, on the same interval on the x-axis. And then here our second octave would be, again, negative sine 2x plus 2. And the only reason I'm moving it up 2 is so that we can distinguish between the first and the second octave. And we could continue on like this. Remember, they were powers of 2, so the next one would have to be half the wavelength of the second octave. So this is going to be positive. This is going to be sine 4x now. We're not doing an arithmetic sequence for octaves. We're doing a geometric sequence. The harmonics had the arithmetic sequences. And so now this wavelength is half that of the second octave. And we'll give it its buddy so that it looks like a proper sound wave here. And then it just would continue on like that in powers of 2. So the next one is sine 8x. And then geometric growth is occurring, meaning that there's exponential differences between the wavelengths of each successive octave. And one more, y equals negative sine 8x plus 6. And so there we have our fundamental octave down at the bottom, and then our first octave after that, our second octave, and our third. We can see the difference here is that the wavelengths, the crests are getting quite a lot closer together with each successive octave as compared to the harmonics, where there was growth or reduction as we moved from the fundamental to the eighth. But it was not in such magnitude as the geometric growth. All right, this has been Dr. T's math class. Thanks for paying attention.